So go back to this one. So you have the inhomogeneous to F. And last time we just in a few lines, we derived the solution, the formula for the solution. You can say it's a particular solution, but this particular solution actually involves, actually has the possibility to add the homogeneous solution. So we can as well just write the solution as F, as Y. So using the form in exercise 7.7.1, because strangely your textbook didn't write down the formula, but anyway, the form is the y sub 2 x integrate x y sub 1. And your textbook use s, but I would usually use exponent. Exponent divided by the long scheme. Exponent the minus 1 integrate x y2 x y f x y dx y w x y. Right, that's the solution. The Wronski is defined as usual. The Wronski is defined as using the same y1 and y2. y1, y2, y1 prime, y2 prime. Right, and last time we solved that. I mean, not last time. One we have divided for the solution for Wronski is some arbitrary constants, w sub a and e to the minus p, integrating p, like x y dx prime and a. We'll probably shouldn't use a, so arbitrary, I mean, because I want to leave the a some constant. I will leave the simple a for the discussion in the green function. Okay. So you know the solution for that one. It only depends on the p coefficient, p for the function p, and with a constant. And so the integration is, I mean, you don't have to use y1, y2 in here. When you actually do the integration, you can use this. Depends on which one is easier, right? You already have the solution for the Wronski. But anyway, let's continue the discussion and transform the form. And first we see that there's a minus sign here. Then the first thing you can do is change x to the lower limit. I mean, at first the lower limits are not specified here, because that gives you freedom to choose the lower limit to satisfy whatever the condition for the problem, say initial condition or boundary condition. So you leave some freedom here, so you choose whatever the lower limit to satisfy your condition. And one particular kind of boundary condition can be easily satisfied using this green function method. This is a so-called two-point boundary condition. So you have a domain X from A to B. So you want to solve your solution Y from A to B, right? And usually the boundary condition is given at two conditions, one at A and one at B. And the usually two kinds, I mean, generally we call it, if you specify Y at a given point, we call it a Dirichlet boundary condition. If we specify the derivative Y prime, we call it a Neumann boundary condition. So you can specify the Dirichlet boundary condition at both points. You set it to 0, or it doesn't have to be 0. So whatever value is fine, and you solve for Y, right? Or sometimes if you set Like you set the derivative to 0, so you set the derivative to 0, you found a solution, right? And to satisfy this kind of boundary condition, we can write it like first integration over the whole range A to B. The first thing is recognize that this minus sign, you can change it to a plus sign by moving that to the lower limit, right? And then the natural choice now is integrate over the whole domain from A to X and then X to B, right? And now you can combine the two. So first you move y2 to inside the integrand. That is allowed. Doesn't matter because you integrate over x prime. You move x inside. Doesn't matter, right? And then you write it like this is integrated a z, and what we call a green function that depends on x is x prime, and then y f or x prime. Right? And by comparing these two, you obviously see that your choice of the green function is like that. The green function depends on two variables. One is x, the other is x prime. X is the variable you express your solution. X prime is the integration variable. Okay, this green function in this case is you have two terms, two parts. One is when x prime is integrating from a to x, which means x prime is less than x. When x prime is less than x, then it's this one. So y2, it's y1, and divided by w. And then the other way around, x prime is integrated from x to b, so x prime is greater than x. We have y1 x, y2 x prime, and divided by w. Is that okay? So can you see that this one is the same as this one, right? So you just write it like that, and you can see that when x prime equals to x, the two will be the same, right? Because both if x prime is the x, both terms are the same. So G is continuous at x equals x prime. So it doesn't matter you just specify the greater or smaller limit. The equal sign is the same for both, right? So that would be the green function is like you integrate. So whatever f, you can now change whatever f is, then your solution just substitute f, your inhomogeneous term into this integral, and you get the solution that way. And that when writing like this, of course, you want to get something out of it, and what you get is an easier way to satisfy the boundary condition. So basically, say if you set x equals to 0, so the ya at the lower limit, right? Then obviously you have x equals to a, then this integral is 0, right? So you get just this term, right? You have y1 a, y1 a, and obviously just involve an integral that involve y2, which is now just a number because you integrate over the whole range. It's just symbolically like that, right? And now if the A is the Dirac boundary condition, and you choose y1 to satisfy the Dirac boundary condition, in particular if you choose it to be 0, if y1, if the boundary condition at A is the function is 0, and you choose your y1, the homogeneous solution such that y1 at A is 0, then this is automatically satisfied, right? And likewise, YB, now the other way around, this will be 0, so you have Y2, integrate A, B, Y1, F. Right? And likewise, if the boundary condition required Y to be 0, you just choose Y2 so that Y2 is 0 at B. And you use this 2Y1 and Y2 to construct your green function. And now, then this formula automatically satisfies the Dirichlet boundary condition at both ends. And it doesn't depend on F now. Whatever F you use, you substitute it to here, you still satisfy the same boundary condition, right? So that's for the Dirichlet boundary condition. For Neumann boundary condition, you specify both to be 0 at both ends. And now you to calculate to find out the Y pi at A and B. Now you need to do a derivative over this one, right? And what you find is that Y pi x is y. So there are two x dependent, the two factors, right? This depends on x in here and depends on x in here. Likewise, depends on x in here, depends on x in here, right? So we first take the derivative over this Y2 and copy that, the other factor. Right. And likewise, using this one, we just take the derivative over Y1. Right. And then take the derivative over this, the upper limit here, lower limit will give you this Y2. And when I take the derivative, just changing all the x pi to x, right? And this is Y1 over x now, from the x and the fx, wx for this derivative. And for this derivative, because it's in the lower limit, you subtract. Right. So you see that these two things cancel. Right. So, so again, you have the same situation as the other two equations here. So Y1, Y pi at A will be, so this will be 0, this term will be 0, this term, Y1 pi of A, and then that integral, and B, Y, U, Fx, Fw, right? And likewise, Y pi at B, Y2 pi at B, because you keep just this term, and B, Y1. Okay, likewise, so you choose, for Neumann boundary condition, now you choose your Y sub 1 such that the derivative is 0 at A, and then you choose your Y2, Y sub 2B here, with the derivative is 0 at B. Okay, then use this to Y1, YB to construct the green function, right? And that would be that we satisfy the boundary condition for any F. Okay, so that's basically the same formula, but you rewrite that and then already incorporate the boundary condition in your formula by this or this choosing your Y1, Y2 accordingly. Okay, so this is like an example for 1D OD or for ODE, then the same idea will be generalized to higher dimension, PDE. I think one of the chapter, chapter 10 or something. Okay. Any questions? So key enough for this one. Right. For now, it's just like a preview of what we will talk about later. Okay.